Okay, now we're going to study our new chapter, chapter 9, which is on convergence in RN. So we want to talk about sequences in RN. We want to talk about functions of several variables. So let's start with some basic concepts of RN. Some preliminary concepts. So this set is defined to be the collection of all the points that has, well, essentially n coordinates, and all those components are real. N here, okay, the number of components is called the dimension. And elements, X, sometimes we put an arrow on it. These are called the points of Rn. Or vectors. Xj are the coordinates. Or components. So obviously two elements are equal if and only if all the components are the same. So this is an element in Rn. Next we have operations between points or between vectors in Rn. So consider two vectors in Rn. And alpha is a scalar. We can talk about the sum of two vectors, which is essentially just adding up each component. Minus with a minus sign. With a minus sign. Number two, a scalar times by one of the vectors. It just use the scalar multiply with each component. Number three, the dot product between two vectors. Alright, so this is the dot product between two elements of Rn. x1, y1, x2, y2. So it's the sum of the product of the corresponding components. So you have a collection of elements in Rn. If you introduce the inner product or together with the inner product essentially gives you a way to measure the size of elements in Rn. So the collection of points together with a way to measure the size of elements in Rn is called Euclidean space. So next we talk about different ways to measure the size of each element of Rn or the vectors in Rn. So X is a vector in Rn. the norm, so this is usual norm, or we call it L2 norm, or the magnitude. Of x is the following number. We use two vertical bar to represent the norm. It's calculated by this formula, square root of x1 squared plus x2 squared plus x sub n squared. Which, by the way, if you notice, this is actually the dot product between x with itself. Okay, the dot product between x with itself. You get x1 squared, x2 squared, and add them up. So that is the L2 norm. And that's one way to measure the size of a vector in Rn. And then we have the so-called L1 norm. L1 norm is essentially the sum of the absolute value of each component. So J here goes from 1 to n. In general, we have the LP norm, which is given by this formula. Each component raised to the power of p, and then the sum raised to the power of 1 over p. So this is the LP norm. Followed by the L infinity norm, or sometimes you can call this the supremum norm of x. The notation for L infinity norm is put infinity here. So this way that we measure the size of this is to use the maximum of or the absolute value of each component. Okay? So let me give you a simple example here. Let's say we have a vector that is given by 1, 2, 3. Its infinity norm is obviously just 3. The p norm is 1 to the p, 2 to the p, and 3 to the p, and then to the power of 1 over p. The p here can be 2, 3, you name it, or even 1/2. And then we have the L2 norm. You can either write a 2 here or just like this, because L2 norm is one of the most common norms that we're going to use. That's the square root, or same as power 1/2. 1 squared, 2 squared, and 3 squared. And this is what we are mostly familiar with. That's the distance that we're familiar with. So once again, I already mentioned about this. Clearly, the L2 norm squared, which is x1 squared and x2 squared, and this sum here, it is actually just a dot product between x with x itself. So this measures the magnitude of x. And if you use x minus y, this actually measures the distance between those two vectors. Okay? Here's y. Okay, here's y. This is x. This is y. So if you take the norm here, okay, that's the size of this vector here. X minus y, as you can recall, refers to this element or this vector here. And you take the magnitude of this, that measures the distance between the endpoints of those two vectors. So now I'd like to explore the properties of norms. Of the Euclidean norm. By the way, Euclidean norm is the same as the L2 norm, okay? L2 norm. Basic property of Euclidean norm. We have the following properties. Some of them are kind of trivial. Some of them are less so. The norm is always non-negative because, well, we're using it to measure the magnitude of something, so it's always non-negative. And it equal to 0 only when x is the 0 factor. So it's 0 for each component. Number 2, alpha times by x. So this you get a new factor. The size of this is the size of x times by alpha. Well, that's not very accurate because alpha can be negative, so we put an absolute value here. Number 3, you add up two factors, you try to figure out the size of it. This is always less or equal to the size of x and plus the size of y. Finally, is x minus y. It's not greater or equal. It's always greater or equal, okay? Greater or equal to, say, x norm minus y's norm. So this kind of reminds us that this kind of looks like the triangle inequalities for absolute value functions. Indeed, the norm, okay, the norm in R2, okay, the norm, sorry, in Rn behaves very much like the absolute value function, okay? So all the properties are the same. So this is probably less trivial, and I like to try to prove this, okay? I like to try to prove this. I'm going to try to take the square on both sides. I square on both sides. Recall that the square of the norm is the dot product between those two vectors. So this is actually a dot product between x plus y and x plus y. Which you can recall the dot product satisfies this property. You can basically FOIL this out, okay? It's the dot product between x with the x and then x with y. Y with x. Those two numbers, by the way, they are the same. They are the same. So that is really the square of the magnitude of x. The middle term is 2x dot y, followed by the norm of y squared. So the question is that really less or equal to the square of the right side? You see, the square of the right side is this, the norm of x squared plus 2, the size of x, times by the size of y, and then plus y squared. So this is the square of the right side. So obviously, to make this true, we need this one, okay, we need this guy to be smaller than the term down here, which turns out to be correct. And this is the so-called Cauchy-Schwarz inequality. So let me make a remark that is indeed true, and we call this inequality Cauchy-Schwarz inequality. Which says x dot y, okay, the absolute value of this, okay, is always less or equal to the size of x times by the size of y. Sorry, there's no square. So I'd like to briefly show this, okay, even though this is probably not very important right now, because one of the more important stuff here is the basic property of all the Euclidean norm. Next time you see this, the norm is always non-negative. If there's a scalar here, you can pull that out, but make sure you take the opposite value here. Triangle inequalities, okay? Cauchy-Schwarz inequality. It's not exactly very easy to prove, okay? It's not exactly very easy to prove. Let me show you one version of the proof. To prove this inequality, let's consider the following trivial statement. I put a variable t here, times by x, and then plus y. I do the dot product between this guy with itself. Alright, obviously this is the dot product between this guy with itself, so this is always greater or equal to 0, because this will be the norm squared, remember? And now I use the property of dot product to FOIL this out. Now apply the fact this is x norm squared. This is y norm squared. So now I like to call this A, call this number B, and call this number C. Yeah. So we have this property, AT squared plus 2bt plus c is always greater than 0. Okay, it's always greater than 0. This is always greater than 0. How can that happen? All right. So here you have a quadratic function of t that is always greater or equal to 0. So meaning this quadratic term on the left side, we will have at most just one real root. Okay, so this means this equation, okay, this quadratic equation has at most one real solution, because otherwise you got 2, then there's a chance that this guy turns out to be negative. One real root. All right. Thus, the determinant, which is 2b squared minus 4ac, will be, it's not greater or equal to 0. Okay, it's less or equal to 0. Okay, less or equal to, if it is 0, that means it's exactly one root. If it's less than 0, that means there's no root. There's no solution. Which is identical to say b squared has to be less or equal to ac. And we write down what b is. You write down what a and c are. Here's what this is. b is x dot y. So the square of this is less or equal to x squared plus y norm squared. Okay. And we take the square root on both sides. That means the absolute value of this dot product, which can be negative, is less or equal to, so sorry, this is supposed to be the product here. Okay, this is not addition, it's a product. The x norm, which is always positive, and the y norm, right? And that's exactly the Cauchy-Schwarz inequality. So basically what we've done is we have introduced what RN is, along with a way to measure the size of elements in RN. And now we talk about the basic topology of RN. So what do you mean by, say, sets? What kind of sets that we have in RN? And what do you mean by, say, a set is open or closed? That kind of thing, okay? Basic topology. We first introduce a few simple concepts. Let's introduce one point. Okay, one point. Let's introduce one point in RN. So if you are talking about R3, there are 3 components. Okay, so this is the A here. We define an open ball. Okay, this set denoted by B, because that's radius, and that's the center. This is defined to be all the x in Rn such that the distance between x and A, alright, I'm taking the norm here, that's the way that we measure the size of it, is less than R. Less than R. Right? And this is called an open ball. Centered at this point A with radius R. Okay? This is an open ball. So what is a closed ball? A closed ball obviously includes the boundary. So here's a closed ball, okay? We put a bar on the top, indicating we're going to include the boundary. The definition is almost the same, almost identical, except we allow this inequality to be equal. Okay, so this distance from x to A is less or equal to R. Okay. So once again, A here is any point in Rn. There's a radius, that's R. So everything inside this, that's a ball, that's a closed ball actually, if you include the boundary here. Alright, so A is the center. So obviously the shape of this ball, okay, the shape of this is not necessarily a ball, okay, depending on the norm, okay, depending on the norm. So let me show you the shape of, well, the so-called ball in Rn with different norms. For example, L1 norm. In other words, I need this L1 norm to be less or equal to R. But let's think about the meaning of L1 norm. I'm going to try to sketch this in R2. Okay, I'm going to try to do this in R2. It's easier for us to visualize. So X is something like 2 component. A has 2 component. Let's try to call L1 norm. L1 norm refers to use x1 minus a1, take Ap's value, and then plus x2 minus a2, take Ap's value. And this list, needs to be less than R, for example. Okay, less than R. Open ball. So let me take A to be. Let's pretend this point A is just the origin. Let's take R is, say, 1. Let's try to visualize this. So the inequality is x1 Ap's value plus x2 Ap's value is less than R. So here's a unit ball with radius 1 in L1 norm. Okay, in L1 norm, it looks like this. Satisfy this. x1 component, x2 component, the absolute value, the sum of the absolute value that needs to be less than 1. Turns out those are all the points inside this square here, okay? And this is 1, this is -1, this is 1, this is -1. You can easily verify that any point inside here satisfies this. So that's the unit ball under L1 norm. What if I decide to measure the distance but use L2 norm? Alright, so you can easily write down the definition similarly. L2 norm looks like this, okay? Square root x1 minus a1 squared, x2 minus a2 squared. That's just how L2 norm is defined. And this needs to be less than, say, R. Alright, so this is the familiar open circle that we're familiar with. Let's pretend A1, A2 once again is the origin. Let's pretend R is 1 again. So you're talking about a real open ball centered at the origin here. So that's under L2 norm. Finally, it's under L infinity norm. L infinity norm refers to the maximum of x1 minus a1 and the x2 minus a2 absolute value. So this needs to be less than 1, okay? It needs to be less than 1. Now, if once again I take a1, a2 to be 0, 0, this is identical to the maximum of x absolute value, and x2 absolute value needs to be less than 1. You can try to picture what does that mean. That means the x1, x2 is always between -1, 1, okay? It's always between -1, 1. This is x1, this is x2. So the maximum has to be below 1. So it turns out this open ball with L infinity norm turns out to be this square here, okay? To be this square here. For us, most likely we'll use the L2 norm, but in practice or in research, a lot of us choose to use L infinity norm or other norms, depending on your needs, okay? Depend on your needs. All right, I guess I wrap up this short section here, and we have a little bit more on the preliminary coming up next.